Every civilization that has ever existed, exists now, or will ever exist, is trapped, not by politics, not by war, not by their own stupidity, by physics, by a law so fundamental that it doesn't care how smart you are, how advanced your technology gets, or how desperately you want to leave. The universe wrote one rule, and that rule says, you don't get out. Now, I know what you're thinking. You're thinking about rockets. You're thinking about Elon Musk and Mars and generation ships and warp drives and all the beautiful, ambitious engineering that clever people are working on right now. And I'm not here to dismiss any of that. Mars, probably doable. The outer planets, maybe. But when I say trapped, I mean something much more specific and much more permanent than an engineering challenge we haven't solved yet. There's a difference between difficult and impossible. Engineers deal in difficult, physicists deal in impossible. And the word impossible in physics doesn't mean we haven't figured it out. It means we've found the edge of what the universe permits. We've found the wall. And this particular wall, the one I want to talk to you about today, isn't made of anything you can tunnel through, go around, or eventually bulldoze with a bigger rocket. It's made of entropy. And before you switch off, because that sounds like a textbook word, stay with me. Because what entropy actually does to any civilization trying to leave its home star system is one of the most brutal, most beautiful, most misunderstood things in all of physics. It's not complicated, but it is devastating. And once you see it, you cannot unsee it. Here's the thing that gets me. We've been asking the wrong question for decades. The question everyone asks is, how do we build a ship fast enough? Speed, fuel, engineering. That's where all the excitement goes. But the right question, the one that changes everything, is what does thermodynamics say happens to any system that tries to do this? And when you ask that question honestly, and you follow the answer all the way down, you end up somewhere genuinely uncomfortable. You end up with a universe that looks less like an open frontier and more like a very elegant prison. Not a cruel prison, not a designed one, just a prison that emerges automatically, inevitably, from the same laws that make ice melt and stars burn out and your coffee go cold. The same physics that governs your morning cup of coffee governs whether any civilization, anywhere, ever, gets to cross the gap between stars and actually survive the attempt. That's what we're going to work through today. Not the engineering, not the speculation, the actual physics, the numbers, what they mean, why they say what they say, and why every serious physicist who has looked at this problem clearly, without wishful thinking, without science fiction in their head, comes away with the same quiet, unsettling conclusion. The stars are not for us, and the reason isn't that we're not trying hard enough. The reason is written into the fabric of reality itself. Let's go find it. People tell me the universe is big. They say it with this tone of wonder, like the bigness is the interesting part. 4 light-years to Alpha Centauri, 2 million light-years to Andromeda. Observable universe something like 93 billion light-years across. They recite the numbers and then stop, as if the numbers themselves are the insight. They're not. The numbers are just the beginning of a problem. And the problem is this. Those distances aren't just far. They're thermodynamically far. That's a different kind of far entirely. That's the kind of far that has a law attached to it. Let me show you what I mean. Suppose you want to get to Alpha Centauri, 4.2 light-years, and let's be generous. Let's say your civilization is genuinely advanced. Not magic advanced, not warp drive advanced, but physics permits advanced. You've figured out fusion. You've built a ship the size of a city. You're going to accelerate to some serious fraction of the speed of light and make the crossing. This is the dream, right? This is what the science fiction writers imagine. And it's not crazy. Nothing I've described violates any known law of physics, yet. So you start doing the arithmetic. And this is where it gets interesting, because the arithmetic has an opinion, and the opinion is not encouraging. To accelerate any object to a meaningful fraction of the speed of light, you need energy, not a lot of energy in the colloquial sense, a catastrophic amount of energy in the precise physics sense. Here's the number that matters. To push 1 kilogram of mass to just 10% of the speed of light, not half, not 90%, just 10%, you need roughly 450 trillion joules. That's about the energy output of an entire nuclear power plant running continuously for 15 years. For 1 kilogram, a human being masses about 70 kilograms. A generation ship capable of sustaining a population masses something like 10 million kilograms at minimum. You start multiplying these numbers together, and you get figures that are not just large. They're large in a way that should make you sit down. But that's not the real problem. The energy is a problem, but it's an engineering problem. Smart people can think about engineering problems. The real problem is what thermodynamics says happens to all that energy. Here's what entropy actually is, because most people have it wrong. They think entropy is about disorder, messy rooms, scrambled eggs, things falling apart. That's not wrong exactly, but it's not the part that matters for this story. What entropy is really about, what Boltzmann figured out in the 1870s, and what Clausius had been groping toward for 2 decades before that, is the number of ways a system can be arranged. Think about a box with 1,000,000 molecules of gas in it. Those molecules are moving. They have positions and velocities. The number of different combinations of positions and velocities those molecules can have is astronomical. We're talking numbers so large that writing them out would take longer than the current age of the universe. Now, most of those arrangements look like the gas spread evenly through the box. A tiny fraction, a vanishingly, pathetically tiny fraction, look like all the molecules bunched up in one corner. So when the gas is spread evenly, and you let it evolve, it stays spread evenly. Not because some rule tells it to, because the overwhelming majority of places the system can go from here also look spread out. The system wanders through possibilities, and most possibilities look like equilibrium. That's entropy. It's statistics, it's counting, and it's iron. Now here's where the trap closes. Every process that converts energy from one form to another, burning fuel, running a nuclear reactor, accelerating a rocket, produces waste heat. This is not a flaw in the engineering. It is not something better materials or smarter designs can eliminate. It is a consequence of the second law of thermodynamics, which is itself a consequence of the statistics I just described. Carnot figured out the maximum efficiency any heat engine can achieve in 1824, and the answer depends on the temperature difference between your hot reservoir and your cold reservoir. The bigger the difference, the more work you can extract. But you can never get to 100%. There is always waste, always. On Earth, this is manageable. You dump your waste heat into the atmosphere, the oceans, the ground. The planet is connected to a vast thermal reservoir, and that reservoir is connected to space, and space is connected to a universe sitting at 2.7 Kelvin, nearly absolute zero, so eventually everything radiates away and equilibrium is maintained. The system works, life exists, civilization functions. On a starship, you are not connected to that reservoir. You are a closed system moving through vacuum, and vacuum is an extraordinarily good insulator. Let me be specific about what this means. Your starship produces waste heat. That waste heat has to go somewhere. Thermodynamics is not optional. In space, the only way to shed heat is radiation, thermal radiation. Every object above absolute zero radiates energy proportional to the 4th power of its temperature. This is the Stefan Boltzmann law, and it's been confirmed so many times in so many ways that questioning it would be like questioning whether dropped objects fall. The rate at which your ship can dump heat depends on the surface area of your radiators and the temperature you're radiating at. Here's the brutal part. As you push your ship to higher and higher velocities, you need more power. More power means more waste heat generated per second. More waste heat means your radiators need to be larger or hotter or both. Larger radiators add mass. More mass requires more energy to accelerate. More energy means more waste heat. You see where this is going. It's not quite a vicious circle, and the math doesn't make it literally impossible to accelerate. But the penalties compound in a way that makes the already staggering energy requirements grow even more staggering. And then you hit the interstellar medium. Space is not empty. I want to be careful here because people often say space is empty and they mean it's mostly empty, which is true, but mostly empty and completely empty are not the same thing. And the difference matters enormously at relativistic velocities. Between the stars, there is roughly 1 atom per cubic centimeter on average, mostly hydrogen. 1 atom per cubic centimeter sounds like nothing. At walking speed, it is nothing. But at 10% of the speed of light, each of those hydrogen atoms hits your ship with the energy of a cosmic ray particle. You are flying into a continuous radiation storm of your own making, at higher velocities, 30, 40, 50% of light speed. The flux becomes genuinely dangerous to any biological passengers, and shielding against it adds more mass, which requires more energy, which produces more heat, which requires more radiators, which adds more mass. The equations don't catastrophically explode. They don't give you infinity and tell you to stop. What they do is something more insidious. They give you numbers that are finite but physically unrealizable. They tell you that to get a 10,000-ton ship to Alpha Centauri in a human lifetime, you need a fuel mass that exceeds the mass of Jupiter, not a large asteroid, not a moon, Jupiter. And that's with the most optimistic assumptions about your drive efficiency. That's assuming fusion, the technology we've been 30 years away from for 60 years, works perfectly and at theoretical maximum performance. Now, a civilization sufficiently advanced might solve the fuel problem. I'm not going to rule that out. That's an engineering problem, and I said earlier that engineering problems are a different category. But here's where the second law reappears and refuses to be dismissed. Even if you solve the fuel problem, even if you find some exotic way to carry or collect the energy you need, the waste heat problem does not go away. It gets worse. The more energy you process, the more entropy you generate, the more heat you must radiate. And your ability to radiate heat is limited by physics, by the Stefan Boltzmann law, by the surface area you can practically deploy, by the temperature your materials can withstand. There is a ceiling on how fast any physical system can shed thermal energy, and a starship operating at the power levels required for relativistic flight crashes into that ceiling hard. This is what I mean when I say the trap is thermodynamic rather than merely engineering. The engineering problems are real. The thermodynamic problems are categorical. They apply to every possible design, every possible material, every possible civilization at every possible level of technological sophistication. As long as that civilization is operating within the known laws of physics, which, so far as we can tell, everything does. Let me put some numbers around this to make it concrete. The sun outputs about 3.8 times 10 to the 26th watts of power. That's 380 trillion watts. That is an almost incomprehensible amount of energy. A civilization that could harness the entire output of its star, a Dyson sphere civilization, the most advanced thing we can physically imagine, would have access to that power budget. And that power budget is, in fact, large enough to contemplate sending ships to nearby stars. The energy is there. The problem is the entropy that energy generates when you use it. Here's the thing about a Dyson sphere civilization. They've surrounded their star and they're collecting its light. What are they doing with that energy? Converting it into useful work, electricity, propulsion, computation, whatever. And every conversion produces waste heat. That waste heat has to be radiated away from the Dyson sphere. The sphere itself becomes a thermal radiator glowing in the infrared. Astronomers have actually looked for this signature, structures that absorb starlight and re-emit it as heat, and found some interesting candidates, though nothing confirmed. But the point is, even a Type II civilization on the Kardashev scale, one that commands the full output of a star, is still subject to the second law, still generating entropy, still constrained by how fast it can dump heat into the universe. And when such a civilization tries to send a ship to another star, a ship that must carry its own energy source, that must manage its own thermal budget in the void between stars with no external heat sink available, it runs into the same wall, just from a different angle. Here's an angle on this that I find particularly striking, and that doesn't get discussed enough. Consider what happens when your starship decelerates at the destination. You've accelerated all the way from your home system, which was already enormously expensive thermodynamically. Now you need to stop. Stopping requires just as much energy as starting and produces just as much waste heat. You can't just drop anchor. There's nothing to drop anchor on. You have to burn fuel in the opposite direction or use some form of mag sail to brake against the stellar wind of the destination star. Either way, the thermodynamic bill doubles. The one-way trip costs you twice what you might naively calculate. Now, why does this trap every civilization? Not just us, with our primitive rockets and our incomplete physics, every civilization, everywhere, forever, because the laws of thermodynamics are not parochial. They're not contingent on the chemistry of Earth or the evolutionary history of humans or the particular way our civilization developed technology. They follow from the statistical mechanics of any system with many degrees of freedom, and the mathematics of statistical mechanics works the same way in any universe where probability works and where energy is conserved. Both of those things appear to be genuinely universal, not just universal in the sense of true everywhere we've looked, but derivable from principles so basic that imagining them violated requires imagining a kind of reality that we have no coherent model for. The second law is not like the laws of aerodynamics, which describe how air happens to behave and which wouldn't apply in a vacuum. It's not like the laws governing nuclear reactions, which depend on the specific particles that happen to exist. It's more fundamental than either of those. It emerges from counting, from the simple mathematical fact that there are vastly more ways for energy to be spread out than concentrated, and that systems evolve toward the more numerous possibilities. Any civilization anywhere made of any materials running on any chemistry is still a physical system, still subject to statistics, still accumulates entropy when it does work, still faces the same fundamental tax on every energy conversion. What this means, taken seriously, is that the universe has a structure to it, a topology almost, that makes certain things accessible and certain things not. Within a stellar system, entropy is manageable. You have a star providing a continuous low-entropy energy source. You have planets to dump heat onto. You have a complex, interconnected thermal environment that lets civilization function and grow. It's not easy, but it's possible. The numbers work. Between stellar systems, the numbers stop working. The distances are so large that travel times at chemically or even nuclearly realistic velocities stretch to thousands of years. Velocities high enough to make the crossing in human-relevant timescales require energy budgets and generate thermodynamic penalties that no physical system we can construct or even coherently imagine constructing can meet. And the relativistic effects that kick in at the required velocities, time dilation, the buildup of interstellar medium into a particle radiation storm, the increasing relativistic mass, don't help. They add complications without resolving the fundamental entropy problem. I want to be honest about what I'm not saying, because intellectual honesty matters here. I'm not saying it's proven beyond all doubt that no civilization can ever reach another star. Physics has surprised us before, and I'd be foolish to pretend certainty I don't have. What I'm saying is, given the laws of physics as we currently understand them, laws that have been tested to extraordinary precision across an enormous range of conditions, the thermodynamic barriers to interstellar travel are not just large, they are categorically different from engineering barriers. They don't yield to cleverness, they don't yield to better materials. They are, in the precise physical sense, prohibitive. There are people who talk about warp drives and wormholes and negative energy densities, and I don't want to wave them away entirely. The mathematics of general relativity does permit, in principle, certain exotic geometries that might allow faster-than-light travel or traversable wormholes. But the word permits is doing enormous work in that sentence. These solutions require things like stable exotic matter with negative energy density, which has never been observed, which may not exist, and which, if it did exist, would create its own catastrophic thermodynamic problems. We don't have a working theory that tells us exotic matter is possible in the required quantities. We have solutions to equations that require it, which is different. The universe is not obligated to provide everything that our equations have room for. And here is the deepest thing, the part I keep coming back to. The same second law that traps civilizations in their home systems is the law that makes complexity possible in the first place. The reason life can exist, the reason stars can burn, the reason anything interesting can happen in this universe is that entropy is increasing but hasn't reached maximum yet. The universe started in an extraordinarily low entropy state. We don't fully understand why, and has been running down ever since. That gradient, that difference between where entropy is and where it's going, is what powers everything. Every living thing is a structure that maintains itself temporarily by accelerating entropy in its surroundings. You eat ordered food and excrete disordered heat. You are an entropy pump. The trap, then, is not separate from the gift. The same law that makes civilization possible makes interstellar civilization impossible. The universe is not being capricious, it's being consistent. The rules that allow complexity to emerge also constrain how far that complexity can spread. There is something almost elegant about this, not comforting, but elegant. The cosmos isn't hostile to life. It's indifferent in a very specific, structured way. It gives you a star, and some planets and 4 billion years and the laws of chemistry and physics, and within that gift you can do extraordinary things, build cathedrals, split atoms, understand your own existence well enough to ask why you can't leave. But the asking is as far as it goes. The understanding is local. The civilization is local. Whether there are other civilizations out there, also local, also trapped, also looking at the stars and doing the thermodynamic arithmetic and arriving at the same conclusion, that I genuinely don't know. The Fermi paradox sits right here in this answer. If life is common, if intelligence is common, if civilizations routinely arise around stars, then the second law says they all reach the same wall. They all find the same prison, and the universe is very large and very quiet, and the silence makes a kind of sense that it didn't before you understood what entropy does to the dream of crossing it. Drop a cup. It breaks. You know it won't unbreak itself. You've always known that, but you probably thought of it as a fact about cups. It's not a fact about cups, it's a fact about the universe. And the same fact, scaled up by factors of 10 to the 40th power, says something very specific about where you will spend eternity. Here, under this particular star, in this particular arm of this particular galaxy. That's not a tragedy, that's physics. And physics at least has the decency to be honest with you about it.